working as coming to my background, and I'm working for STA and PNR and fixing of timing and flow setup issues, and if there is any flow issues, right, we are fixing those issues. And my main responsibilities are like developing from the floor plan till sign off STA, IR analysis running. IR analysis, timing analysis. So as a part of today, we are going to discuss static timing analysis. So what is static timing analysis? So uh, this is not my projects, and I work with different projects. I work with 28 nanometer, 24 nanometer, and recently I worked with 3 nanometer technology with Sign. So static timing analysis is a key intention we need to learn in PNR. If you wanted to become a PNR engineer, it is a key role. It is not a role. It is a responsibility of a PNR engineer to know about static timing analysis. So if you got any doubts, right? So just stop me there, so you can discuss with me. So be like a treat me as your friend, just I can say it as. So that is uh, my background. So coming to static timing analysis, so why we are doing static timing analysis, and what is static timing analysis? Static timing analysis is performed based upon the worst case inputs. So what are these worst case inputs? So whenever we are giving the input delay high. So if I am delaying the input high means, so that is input delay is more. What does it mean? So input is taking more time to come to the flip flop or any combinational circuit or any logic inside my module. So do you all know module, right? So if doesn't know, I can explain from the how the module look like, and what is the module, what is a block, what is a core, and what is a top. If you guys don't know, I can explain from the basic point of view. If you guys know, I can proceed with that. Okay. Hello. Yes, feel free to
Just
interact.
yeah, please interact with sir. Tina, Punika, Pooja, Harish.
So just whatever you know, guys, right? So from there I can take. So at least you have a better idea of what I am telling. So if you don't know, right, just tell me don't know, so that I can discuss. Okay. I can give a brief introduction of that. Okay. Hello.
Yeah, just continue. Continue.
Okay. Okay. I'll explain that thing also. So what is let me take a paint. So can you see my screen, right? So this is my top. Okay. So in the top there is core. Core is nothing but a core area. In this core there are different types of blocks. Uh, so block level implementation, blocks are going to implemented by block owners. So some blocks will be there like this, sitting like this. So we don't run all the blocks combinedly. We run individually. This block wanna run one block. I handle two blocks. So if I handle two blocks, right? So these two blocks are mine. So and whenever we are working with core, right? So whoever works with core, so they are going to integrate on the top, integrate, and they combine with the top. In the top, what we have like bumps, you'll be seeing like circular type of things, and IO pads. So like this it will be looking like. So this is a just brief introduction of these things. So in each and every block, so this is one, let us take this A block. So in this A block, I am telling this A block. So in this A block, right? So this is A block. Okay, block A. In this, there are different types of modules. There are different two modules, three modules, or and there are some memories also. Memories also sitting in the floor plan. So this is a rough diagram. So if you got any doubts, right, just let me know. So in this module, there are different types of memories, modules. In modules, what will be there? There are standard cells. Okay, in module there are different types of standard cells. Standard cells are nothing but AND gate, OR gate, XOR gate. These types of gates are known as uh, basic gates, right? So we know all these things. So like this is a combinational logic, I can say. Combinational logic, and the flip flops also will be there inside the module. Okay, got it right? Okay, let me come to the topic. So So in this, what I said, so we are giving the worst case inputs at the input side. So why we are giving worst case inputs? So if my chip is operating in the worst case, right, it will operate in the best case also. It will operate in typical conditions also. So we had three types of mainly I can say. So there are different types of corners: worst corner, best corner, FF corner, SS corner, and typical corner. So if we are, so what are the worst corners are like FF corner and SS corner. What are these corners? We discuss in future, like upcoming slides. So if you got anything, you just let me know. So we are analyzing the timing. So how we are analyzing? We are analyzing the timing based upon the maximum values. So SS corner, SS corner, just make a note of these things. So it will be easy for you. So SS corner will have max delays. So why SS corner will have max delays? So this is an interview question. You can make note of it. So why SS corners will have max delays? So because whenever we are implementing these SS corners, right? So these SS corners are given by standard cell team. So there are some libraries, okay? SS 1.1, SS 0.9, and SS 1.7. Share slide 2. Okay. So if you are doing with SS corner, right? SS corner is nothing but uh, whenever we are doing with SS corner, in SS corner we have different voltage also. I'll show you that voltage also in future slides. And why we do SS corner analysis for setup. Okay, just make note of it. So why we are doing was in setup analysis, we are
Hello.
delaying the combinational data.
Hello.
Hello.
Actually, it's seeing the only first slide only.
Yes, Harish.
Actually, right now we are sharing the which slide because we can see the only first slide.
Yes. I'm still saying this thing. So I'm just introducing the worst corners. What are FF corners and SS corners? Okay, I'll show you those slides also. Just I'm just making note. You can note these points. SS corner for setup analysis and FF corner for hold analysis. Okay.
Yeah. Okay.
Okay. Just for information. Okay, so these delay values will be max delay, min delay will be present in SDC. Do you all guys know SDC file, right? So generally these SDC files are given by synth team, synthesis, right? Whoever the run the synthesis, they used to give the synth, and they will be coming from the RTL people. So you know RTL people, right? So if you know the VLSI flow, you can get to know that RTL people who are RTL and what they are doing. So if you want, I can take a one of the class on that also. So okay, and these are no input vectors applied. So why we are not giving the input vectors? So anyone can say, just for your interaction only. So why we are not giving input vectors first? Because if we are giving input vectors, right? So then we are checking the functionality also, but we don't need the functionality. We just wanted to meet the setup and hold time here. So if you are doing with giving inputs and checking for the timing, right, it will take more time, more than expected. So if STA is running within 1 hour or 2 hours, it will take DTA. DTA is nothing but dynamic timing analysis. So if you see the slide, right, so DTA and STA. So DTA, while working with DTA, right, we need to give the input vectors also. So input vectors, how we will giving was based upon the patterns. So I'll show you the pattern how it will be looking like. So this is one of the block. Let us take. So these are the inputs. So 1, 0, 1, 0. This is 0, 1, 0. Okay, so this is one of the pattern. So like this, we need to give all the patterns to all the inputs. Okay, so it will, we are checking one pattern, we are giving one pattern and checking the timing. We are giving other pattern and checking the other timing. So it will take more time, right? Obviously. So when our 111 is given, all the, like, we need to, right, all the combinational inputs whenever we are giving 0 0 0 1 1 0 1 1, like that. So it will also looking like a same. So it will take more time than expected. This is what DTA is. Okay, okay, guys. So here we can check the quality of the netlist and the what we are checking, whether the functionality is good or not. So functionality. So in STA we can't check the functionality. We are just giving the input where we are just giving the SDC and all these things and telling the tool that check for the worst case and the best case of the timing, so that we can we will be getting the violations. So whatever the matched fan violations, fan out violations, and other violations will be getting, right. Clock related information also need to be given. Since why we need to give the clock related information? Any guess? Since why we are giving was to know the how tool is going to know without giving the clock related information. So it need to calculate, right, how the setup is how the setup is coming, how the setup is working, all these things. Okay, so I'll take one slide and oh shit, this is, I'll take one paint and so this is one of the launch flop. So this is the combinational circuit. So one of the clock is coming like this, another clock is coming like this. Okay, so whenever the data is, if I launch the data here, D and clock, this is clock. Okay, so whenever data is launched here, so data is launching here, right? So whenever the clock comes, right, whenever the positive, do you know how the flip flop works, right? All people. So let me explain. Whenever the positive edge of the clock comes here, right, then the data will be, whenever the whenever the positive edge of the clock comes here, then data will go from here to here. Okay. Okay, then data will come here, and here it will check for the setup time. Okay, at this edge we are checking for the setup time. Okay, Whenever the data is launched here, right? So we are checking for the setup at this edge. What is this? Capture edge. So we say it as capture edge. Okay, make note of it. So if you guys can't understand, just let me know. Whenever the data is launched here, right? So we are uh, capturing the data here. So why we are checking this edge only? Why we are not checking this edge? Anyone can answer? Anyone? This is the interview question. You can try. So I am telling the answer also. So why we are checking was, so once let us take, I launched 0. So this 0 came here. Okay. At the first edge, I 0 came here. So in the next edge, I am launching 1. Okay. Next positive edge. So next positive edge will be coming, right? At next positive edge. So before this capturing, if I launched this one, right, what it will be happening? This 0 won't be there and 1 will be coming here. Okay. So this 0 is not captured by this flop. Okay. This captured flop, 2 flop. This is 1 flop. Let us discuss. So this is not captured, this data. This 0 is not captured by this flop. So what it is meant by was meta stability. Just make note of this thing, just to remember these things. So these are the main terminologies. Okay. So what it is, what does it mean was, if one of the data is launched from the launch edge but not captured by the capture edge, what does it mean? The data is overriding somewhere in this combinational loop or somewhere in the flip flop or anywhere. So it need to be so data need to be stable for some time. Okay, before the rising edge of the clock. Do you know setup and hold time definitions, right? We'll discuss that also. So we are checking for the quality to increase the input test vectors, and clock related information is also given. So in both the cases, clock related information is given, and simulation time is more. That is why we don't prefer DTA. And here no simulation time, since we don't have input vectors, and it is easy for us to calculate. It is used for synchronous and asynchronous as well, DTA, while it is only suitable for synchronous designs only. So just make note of it. If you can want, you can prefer anytime. So synchronous is nothing but whenever clocks are coming from same PLL. PLL is nothing but clock generated. So clock generator, we say it as in VLSI terminology. What PLL is? Uh, this is generating the clock. Okay, clock generator is known as PLL. FPLL we say generally. So it is only suitable for asynchronous. So whenever two different PLLs will be there, right, then two different clocks will come. Obviously, that is an asynchronous. Okay, suitable for having clocks, multiple clock domains. Yes, as you said, right? As we said, it is suitable for multiple clocks. Multiple clocks are nothing but if you are having two clocks. Clock is getting clock 1 and capture clock is getting clock 2. Clock 2. Okay. Clock 1, this is 1. It is. So in between that, there is combinational data. Okay. So this is an asynchronous circuit. Okay. Got it, guys? This is what asynchronous is. Before that, I have showed you, right? Same clock. These both are connected. This is synchronous. Okay. Okay. This is suitable for asynchronous and synchronous. Okay. Multiple clocks and suitable for clock crossing. Okay. And computation time is more in DTA, whereas computation time is very less, and more pessimism, like more accurate in this STA, giving maximum delays. So we are giving the maximum delays and we are checking for that, right? So this is more pessimistic. So like not exactly the number we are not getting. So we are getting an approximate value. Okay. We are getting just an approximate value, since this is we are doing it for in long time back they used to do DTA, but now nowadays they are not doing DTA. Even this is more pessimism, but this is a more optimistic. Optimistic is nothing but good good values it is giving. Okay. Pessimism and optimism. Okay. Why STA? STA takes less time compared to DTA. It enables designer to verify the design meets the constraints. Do you know constraints, right? Constraints are nothing but SDC constraints. Uh, why we need SDC constraints was how the my design is operating. Design is operation is more, right? So how my design is operated when so I'll give you an example. Okay, this is one of my block. Okay, uh, just say some block name is X. Okay. Oh shit. So this has some inputs. Okay, let's make it as pins. Okay, so the last pin is clock. Generally we don't take clock as last pin, but for example, so I need to tell that this pin, this is input pins, right? These are input pins. Input pins to this block. Okay. So these input pins are triggered with respect to this pin. Okay. If clock is 1 nanosecond. 1 nanosecond means if the clock is taking 1 nanosecond at the time period. Okay. So then input should be re, released at 0.1 nanosecond. Okay. With respect to clock, we need to say this input delays and output delays. Okay. So after with respect to after clock generated, the after clock generated within 0.1 seconds, 1 nanoseconds, this my input need to be triggered. That is what SDCs are going to say. Okay, just say these things. It is better. This these are the key points of STA. STA helps to designer to design and perform the critical paths and potential timing violations. So let me explain you one thing. So in one path, this is an interview question. Just you can think of it. One path, there is a both setup violation and hold violation. Is it possible? Anyone? Just try. You know setup time and hold time, or do I need to explain, guys? Just interact with me so that I can know what you guys are.
Yes, sir, we know.
Huh?
We know, sir.
You
The
know, right?
setup and hold time. Yeah.
Okay, okay, sure. Okay, so one of the question was what is setup time? Like setup time and hold time they asked. So why we are getting in same path both setup and hold time? The question was okay. So one of the root cause it may be was, I'm saying the answer, you can make note of it. So one of the root cause was constraints are not good. There may be chances of constraints are not good, and a proper clock is not built. Okay. Skew is skew. You guys know skew, right? Whoever taught you the PNR concepts, right? Those guys will tell you about the skew. Uh, just if you don't know, just let me know. I can explain. Okay, if skew is more, if latency is more, latency is also comes under PNR. So if anything you don't know, just let me know. I can explain. Okay, I can give my best. The latency, if latency is more, even if interviewer will cross question you, so all the things are good and constraints are good, so what may be the other root cause? Just guys make note of it. So I felt this question, I fall with this question. For every interview this question is a common question. I'm really saying this thing. So as you guys said that setup and hold time, you don't know. So this thing, the one of the root cause was crosstalk. Crosstalk. I'll explain you how crosstalk is affecting the setup and hold time. Okay. Do I need to explain, or I need to explain setup and hold time first? After that, this thing. How do you need? Guys, feel free, because this is your career. I can't say anything. So here, so my data is launched here. Okay, my drawing is bad. Don't. My data is launched here, and if it should be follow like one thing. The before After the rising clock edge, the data should be stable. The specific amount of time the data should be stable. That is known as hold time. Before the rising clock edge, the time before the rising clock edge, the data should be stable. Okay, this is setup time. Okay, we need to check hold time at each and every edge. Okay, we need to check the setup time at the capture edge only. Capture edge only, not in the launch edge. So we can check if there is one flop behind it, then we can check. So no need to check actually. So it is not a compulsory check, you can say it as. So where we are checking this edge, when there are some group paths, I'll say that group paths also, then we are checking these things. Okay, uh, this is how the setup time and hold time. So as I said, right, why crosstalk is affecting setup time and hold time. Do you guys know crosstalk or don't know? Guys, answer. You don't know, right? Even I explained also, it won't be helpful for you. So uh, one of the net is this one. Okay, so in parallelly, one of the other net also sitting here. So what it will create in between, that one thing will be creating? What is that? Anyone know?
That's crosstalk.
Yes,
And
crosstalk is
it will, yeah, it will create some distortion in the clock signal.
yes, distortion. How you will be getting? There is one thing forming between these two wires. You can see
Capacitor.
straight, right? Yes, correct. We say it as coupling capacitance. You're correct. Nice. So due to this coupling capacitance, there may be difference in launching and capturing edge of the clocks. Got it right? So there may be a delay. This net can introduce delay on this net, or early delay or late delay. So early means the clock will come earlyly, fast. If both are switching in the same direction, what it will do? If this one and this one are switching in same direction, so what it will happen? So this net will be fast and the clock will come fast. Okay, clock will come fast. So clock coming fast means how it is. You guys know the setup equation and hold equation. So I'll explain that also. Okay, so due to these effects, this is creating the crosstalk and degrading our design, performance of our design. Okay, so we need to take care of these all the things. Okay, and other things, uncertainty values, and uncertainty is nothing but skew plus jitter plus margin. Okay, that is one of the thing we need to take care. And latency, tran issues. Tran issues, you know, right? Tran issues, actually, this is one cell, standard cell. Let us take. So standard cell will have one input, and let us take. This is not there. It will have two inputs and one output actually. So uh, So based upon the input tran we are giving, right? The cell delay, how the delay is going to be calculated was cell delay. This is some AND gate. Okay, AND gate delay is based upon calculated on input tran and output capacitance load. So how this is connected to the output capacitance load. So this AND gate will be placed in my design, right? So how the output, how much is the output capacitance? Based on those values, it is going to take the cell delay from the library .lib file. Okay. .lib is nothing but in these values, based upon the input tran and output capacitance, these values are taken. Okay.
But what is the meaning of standard cell you have mentioned here?
Nice question. So standard cell is nothing but a cell. You know AND gate, OR gate?
Yes, sir.
No, those AND gate, OR gates are nothing but standard cells. All combinational cells are the standard cells. Like AND gate, OR gate, XOR gate, XNOR gate, inverters, buffers, clock inverters. Uh, these all things are comes under these standard cells. Okay.
Okay.
Got it?
And sir, the crosstalk in the previous circuit, it may also affect the input signal, isn't it?
Yes. So
We are
crosstalk
not
is not
considering
only
that.
for the clock only, it will affect the input signals also. So this is an example I said. So not only clock path, it will affect the inputs also. If the one of the net is here, right? So it may affect this like this also. Input net also may fail. Input net, this is input, right? This is D. Hello?
Yes, sir.
Do you got it, my point, right?
Yes, sir. Yes. Got it.
Okay. So crosstalk is not only affecting clock to data, and it is affecting clock to data also. Clock to data nets also which is going to affect. There may be chances of this to this also. Anyhow, it may be chance. Okay. This is one of the question also. Okay. There are so many questions here. You need to know these things while attending the interviews. And STA inputs. What do we need as an STA input? So, okay, .v file. .v file, you guys know, right? Verilog file. What does Verilog file? Anyone can say?
Sir, I think relog file is the design file.
Yes, correct. Yes, the design file. It is a net list. Okay. In that net list, you will be having the how the standard cells are connected, how these are interconnected, and how the memories are connected with standard cells, and all the design related informations will be there. You are correct, man. And SPEF. SPEF is nothing but RC extracted data after post route. You guys know post route, right? Post route is a part of PNR, so that is why I'm not taking out. And if you want, I can say from the PNR. If anyone want, okay. So after post route netlist, what we do was we take the def from the post route and we do the QRC extraction. We do it as PEF extraction. So and the SDCs will be common. SDCs won't change normally. Like the whatever the synth SDCs will be there, right? Though those STCs only will be there, but corners are going to add it. So for one corner, one STC, one corner, other STC, like that it will be needed. SDFs are not needed. I don't think SDFs are not needed. SDFs are the outputs of the STA, not the inputs. Oh, dot lib, timing dot lib. As I said, right, dot lib.
Yeah, you can start.
Can I start? Okay. And dot lib and dot spef and whatever inputs, right? All our inputs are common, whatever we are taking in the PNR side, right? Those inputs are needed here also. So outputs are generally the reports and SDF. So SDF is one other output. Dot SDF, it is another output. And timing. This is, do you know timing exceptions, right? This is generally in synth level. They used to say that false path, multi-cycle path, disable timing. These paths are there. So I'll show you that thing. This is MCT. MCT is nothing but multi-cycle path. So if the data is taking more than if data is launched at this edge, right? If the data is it should be captured at this edge. But if it is taking more than one edge, right? Then you say it as a multi-cycle path. So this is a multi-cycle path. Okay. If it need to be captured here, but it is taking more than this cycle. So then hold will check here. But we are checking for the hold at same edge, right? As I said, if you remember, if hold data is launched at 0, it need to be checked at 0 only. But in MCT, we are checking here. Okay. And HCT is nothing but half cycle path. So here, if you see here, right? If you zoom this thing, you can see this thing, right? This is a positive edge. This is a negative edge. So how the waveform look like? So my data is launched at positive edge. It is checking for the next negative edge. Okay. Next negative edge. This is okay. Falling edge. So it is not checking at this edge. Setup is checking for this edge, and hold will be checking for the before edge. Got it? So, yes. Any question?
मैं गाजीपुर में।
Hello. Set disable timing. So why we are doing this thing was whenever there are different types of clock domains, right? I said you clock 1 and clock 2. Then we do this reg 1 to reg A to reg B. Then no need to we are telling the tool that no need to check the timing for these two paths, two flops, reg A to reg B, or some reg pin to reg pin. So we need to mention the pin here, not the cell name. So okay, it will be looking like reg A slash CP reg B slash CP. It will be looking like this. Okay, whenever you are giving that path. Okay, false path. False path. It is not a real path. It is just a fake path. So we need to tell that don't calculate the timing for these paths. So it is not required. So then what it will do is tool will try to optimize while doing the PNR stage itself. We need to tell these things to tool. So don't calculate the timing for these paths, and don't add any buffers. If you are not saying the tool right, it will obviously try to add some buffers and try to balance the delays and try to meet the setup and hold times. So we need to tell the tool. So the false path will be 0 to 1 here and 1 to 0 here. Okay. Checks in STA. What are the checks we need to do in STA? The checks are analysis modes. So the what is an analysis modes, you know, right? I'll I'll say that thing. Analysis modes is nothing but one mode. Mode means funk mode, scan mode, and sleep mode. There are different types of modes. So what this mode is nothing but if a block, if a block I have the one chip, okay. So if it is operating in a functional mode, so if you are turning on your phone, you are seeing the screen, right? So then what it is doing, it is in a functional mode, okay. Whenever you again you if you click the power button, right, it is going to a sleep mode, right? So there are different types of modes. So these are the modes, okay. Like we need to tell the two whatever the modes we taken, right, whether the timing is meeting at all these modes or not, we need to check that thing, nothing else, just for data to data checks. So anyone know this data to data checks? uh, and data to data checks is nothing but if a flop has two pins D1 and D2, then we need to check for the setup and hold for those pins also. I'll tell you like this. This is a flop, okay. This has D1 and D2. Then we need to check for the setup and hold for these both, okay. And case analysis. Case analysis is nothing but we are disabling the clock, right? Sometimes we don't want the timing to check, like for some cases, for some launch enable or launch, I mean latch. Like there is a latch, right? Then we use the case analysis. Okay. Uh, if the multiple clocks are for a register, so I'll show you. So if the clock 1 is coming here, at the same time, if the clock 2 is also coming here, misrouting, there may be a chances, right? So we need to see that these type of conditions shouldn't be happen. Multiple clocks are occurring for a same register. Min pulse width. Min pulse width is nothing but, so there is a one rule in while implementing the CTS stage, we need to take care of these things. So let us take, my clock period is 1 nanosecond. Okay. What does it mean? This is 0.5, 0.5. Okay. This is 0.5. Okay. So the min pulse width, it should say like it should be minimum of 0.5. This is rise pulse width and width, right? So my mean pulse width should be greater than or equal to 0.5. If it is less than, right, so then there will be getting the frequency errors, like the performance issues. So it is not meeting the frequency. We can say that these are timing issues. So this may lead to setup time and hold time issues also. We need to take care that mean pulse width variations. Okay. Derived clocks. Derived clocks are nothing but generated clocks. Generated clocks, you know, right? A clock divided by 2, clock divided by 4. From the master clock, there are some divided clocks. So we need to take care of those things also. Clock getting checks. Clock getting checks and setup time and hold time checks. And clock getting checks, you know, right? Clock getting check is nothing but this is a special technique. This is used. Okay, I will explain this thing. This is one ICG cell. You can see in net also the same thing. ICG cell. So why these clock gators are used? This is one block. Okay. These are the input for clock gator cell. So what this clock gating cell is doing was, whenever the clock is needed only, then only it will give the clock, or else the clock is going to be shut down. Okay. Meantime, only 2 pulse widths is given. So if I wanted to only give these 2 pulse width, then only I'll specify that I need only these 2 pulse width, so that I can save the power, right? So this is one of the power reduction technique, you can say it as. Okay, ICG cell will protect so much power. It will protect like so much milliwatts. Okay, so it is one of the main advantage of in lower nanometer technology. So this cell is a best useful technique, you can say this. So while giving this thing, right, so we need to check for the setup and hold time also. This clock is getting to this block, right? This clock, whenever this clock is given to this block, we need to check for setup and hold time. That is the main thing. And skew and insertion delay, as I said right before, as a PNR engineer, we need to check this thing. Clock removal pessimism. So anyone know this thing? Let me explain this thing also. So CRPR, we say it as generally. Guys, feel free to ask me any type of questions. Okay, this is not a small concept, and I am expecting. You can expect so many questions in interview also. This CRPR is nothing but this common path is there, right? This is common for launch as well as capture. So this is a capture path. As I said, this is a launch path. Okay, this path, in this path we are applying the D rates. How we are applying the D rates? Why D rates are applied? Anyone can answer? D rates, you know, right? Or don't know? Yes, are you there? Okay. Why D rates are applied? Basically, someone is speaking. Why D rates are applied? Basically, to improve the pessimism, or to give an whenever there is an whenever there is a my chip should be operated at Hyderabad as well as in Himachal Pradesh, right? So we are giving the worst conditions so that while implementing itself, we can't we can't create an atmosphere, right? So we are giving these D rates such that we are closing the timing at these corners. This is one of the reason we can say it as, and we can other reason what we can do is what why D rates are applied was whenever I am giving confidence that to customer that even if it is if there is if there even if there is small deviation in input or output, there won't be causing any timing violation. Just make note of it. Even there is any timing like timing deviation at input or output or clock, you don't get any timing violation. That is what the confidence we need to give to the customer. Okay, customer is nothing but the chip owner who is dealing with that chip. Okay, so while dealing with this, right, in setup we give the max values here in the data path. For setup, this is the same way. Hold also will be looking like this only, but it will be in the contrast opposite. In for setup, if I'm giving the mean value for this. Okay, so why I'm giving these values? Anyone guess? So my equation is t should be greater than, this is a setup equation, TCQ. This is TCQ. This is TCQ. Okay, and TPD. TPD is the combinational delay. Okay, and T setup. This is for the setup of the capture flow, as we discussed it, right? This is for TCQ plus TPD. TPD is the combinational delay plus setup time. So what I am doing was I am operating in a opposite contrast. Like I am giving here, if we given max here, right, we are increasing the clock period. Obviously, this equation will pass. I am giving in a contrast manner. Just check this thing. I am giving a min value at here. Okay, I am giving the max value at here. So what does it mean? Into deviate from the equation, deviation from the equation, so that these D rate values are applied in an opposite manner to this equation. Like you guys know this equation, right? Okay, this is how the D rates are going to check. So whenever you are giving like this, right, here this path will be there, right? Clock removal precision, CRPR we say it as. So both min max delays will be there and this path. Okay. So then what how it will do was max minus min value. Okay. Is the delay in the cells, delay of the cells here, whatever the cell sitting here, right? So those delays are these things. And worst slew pessimism and the debugging delay calculation, and debugging delay calculation is simple, quite easy. You can there is some comments, I can say those things, and setup and hold and noise. How noise can be debugged? Any guess? Anyone? So noise is nothing but just a crosstalk only. Crosstalk noise we say. Okay. Design constraints check, as I said, right? SDC check. Okay. Case analysis. So case analysis, just telling tool that circuit is operating in different condition. So if circuit is operating in different condition, right, then we need to say the tool that this scenario, this latch should be turned on. This scenario, the latch should be turned off. In some scenarios we don't need the latch. So some scenarios we need the latch. In future case analysis we can see those things. And as we know, right, as I said initially, if you see the fast corner FF 1.15V 125C. 125C is nothing but temperature. Okay, this is RC max and RC min. So what is this RC max and RC min? Any guess? So RC max and RC min is nothing but, so that is a QRC, like whether that resistance is high or capacitance is high for the metal based variation. These are okay. These are actually the metal based variation. So as I said, you right, process is nothing but generally this will take some time. So if you guys wanted to continue, or should I stop? Just because process, voltage, temperature, it will take some more time. Okay. So while in process, what we are doing was the NMOS and PMOS. We are controlling the speed of these MOSes. Okay. So in PMOS, there is some we can control this PMOS, like these are given by fab people, okay, and not by us. So we are trying to control these things. Uh, process corners describe the extreme case variations. These are generally given by the fab people, and we just take those files and we just put it in our run. If a design works in all corners, it will probably works in any variations. Okay. So what we are doing was, if my design is working at fast corner and slow corner, right? If it is working right, it will definitely work in slow fast and fast slow corners. So what is this fast corner? Okay, just guys make note of it. Fast means fast PMOS, fast NMOS. Okay, slow means slow PMOS, slow NMOS. Okay, guys, this is more important. Okay, if anyone didn't understand, okay. And the voltage 1.15V and 125C and 125 or 165. Generally you use 165. No, 125 we use. And M45 means minus 45. Okay. This is one of the thing. And temperature also we need to take care. Design margins. This is nothing but the, so like how the variations will be looking like in whenever there is this threshold voltage will be there, right, for the MOSFET. So how it will be. Yeah. So if you see, right, cycle time slow, VDD is slow, temperature is slow. This is how it was looking at process variation and temperature variation. And that's it for today. And if anyone has any doubts, I can. Guys, are you there?
Yes, sir.
Anyone has any doubts? Hello.
Yes, sir.
Yes, you can ask.
No, sir.
Shahid.
Don't have any question.
Huh?
Don't have any questions.
Which question?
Sir, I don't have any question.
Okay.